In this class, we will study the algebraic method to solve linear programming problems. We will begin by considering a maximization problem subject to less than or equal to constraints. We will look at the same example that we used to illustrate the graphical method. So, we go back to the same maximization problem which maximizes 10x1 plus 9x2 subject to 3x1 plus 3x2 less than or equal to 21 and 4x1 plus 3x2 less than or equal to 24, x1 x2 greater than or equal to 0. Now, in order to solve this algebraically, let us first look only at the constraints. For a moment, let us set aside the objective function, and for a moment let us set aside the non-negativity. So, we are looking at 3x1 plus 3x2 less than or equal to 21 and 4x1 plus 3x2 less than or equal to 24. So, we have two inequalities. So, at the moment let us again assume that we know to solve equations while we do not know at the moment to solve inequalities. So, under the assumption that we know to solve equations, let us see how we can apply that idea to solving the two given inequalities. So, in order to solve them as equations, the first thing is to write them as equations from inequalities. So, we have 3x1 plus 3x2 less than or equal to 21 and x1 x2 greater than or equal to 0. So, if we have to satisfy x1 x2 greater than or equal to 0 and 3x1 plus 3x2 less than or equal to 21, it is now possible to introduce another variable called x3 and write 3x1 plus 3x2 less than or equal to 21 as 3x1 plus 3x2 plus x3 equal to 21, which is what we have shown here. We have written 3x1 plus 3x2 plus x3 equal to 21. Now, since x1 and x2 have to be greater than or equal to 0 and they have to satisfy 3x1 plus 3x2 less than or equal to 21, therefore, 3x1 plus 3x2 can either be equal to 21, in which case x3 will be equal to 0, or if 3x1 plus 3x2 is less than 21, then x3 will take a positive value. Therefore, x3 will now be defined as greater than or equal to 0. So, x3 is greater than or equal to 0. So, 3x1 plus 3x2 less than or equal to 21 is now rewritten as 3x1 plus 3x2 plus x3 equal to 21. It is written as 3x1 plus 3x2 plus x3 equal to 21 and x3 greater than or equal to 0. In a similar manner, 4x1 plus 3x2 less than or equal to 24 is written as 4x1 plus 3x2. So, it is written as 4x1 plus 3x2 plus x4 equal to 24 and x4 will be greater than or equal to 0. Now, x4 is greater than or equal to 0 because if 4x1 plus 3x2 is equal to 24, then x4 will become 0. If 4x1 plus 3x2 is less than 24, then x4 will take a positive value, therefore, x4 is greater than or equal to 0. So, the given problem maximize 10x1 plus 9x2 subject to 3x1 plus 3x2 less than or equal to 21, 4x1 plus 3x2 less than or equal to 24, x1 x2 greater than or equal to 0 is now written as maximize 10x1 plus 9x2 plus 0x3 plus 0x4 subject to 3x1 plus 3x2 plus x3 equal to 21, 4x1 plus 3x2 plus x4 equal to 24, x1, x2, x3, x4 greater than or equal to 0. Now these variables x3 and x4 that are written here, these variables x3 and x4 that are written here are called slack variables. Now these slack variables are used to convert an inequality into an equation. So this inequality is converted to an equation by the addition of slack variables. Now when we formulated the problem, we said the revenue associated with x1 is 10, the revenue associated with x2 is 9. So the revenue or profit or money that is associated with x3 and x4 are 0. The money associated with x3 and x4 are 0, and it is assumed that they do not contribute to the objective function. Now we have converted a problem with inequalities into a problem with equations, and we now try to solve this problem. Now we started by saying that since we know to solve equations, we will now look at these two equations and try to solve them. So we have two equations, but now with the addition of the two slack variables, we now have 4 variables x1, x2, x3 and x4. When we learnt methods to solve linear equations, we learnt methods where the number of variables that we solve is equal to the number of equations. But now in our example, we have 4 variables and we have 2 equations. Now when we have 2 equations, we can solve only for 2 variables. Now we have to find out a way by which we solve for 2 variables at a time when we have 4 variables and 2 equations. So let us now see how we solve this. So the problem that we have now we are now going to solve is given on the right hand side. The problem that we are going to solve is given here: maximize 10x1 plus 9x2 plus 0x3 plus 0x4 subject to the first equation here, second equation here, and so on. So there are 4 variables and 2 equations, and since we have 2 equations, we can solve only for 2 variables at a time. So we choose 2 variables that we are going to solve, which means the other 2 variables that we are not going to solve, we have to give them some value. For example, if we assume that we are going to solve for x1 and x2, we need to give some value for x3 and x4. If we give a value of 1 for x3 and x4, then the equations will become 3x1 plus 3x2 equal to 20 and 4x1 plus 3x2 equal to 23. If we give 0 value for x3 and x4, it will become 3x1 plus 3x2 equal to 21 and 4x1 plus 3x2 equal to 24. So we have to give some value for the 2 variables that we are not going to solve, which are called fixed variables. We have to give them some value. Now we can give any value to x3 and x4, except that we want x3 and x4 to be greater than or equal to 0. Therefore, fixing x3 and x4 or fixing any 2 variables, we can do it in infinite possible ways. The easiest thing to do, and perhaps the first thing we can try and do, is to fix these variables at 0. So what we are going to do is, at any point we are going to solve for 2 variables by fixing 2 other variables to 0. Those variables that we are going to solve are called basic variables, and those variables that we are going to fix to 0, we are not going to solve for these, they are called non-basic variables. Now, we have a total of 4 variables in this formulation that we have on the right hand corner. So, we have 4 variables in this formulation that we have. There are 4 variables. At any point I am going to solve only for 2 variables and I am going to fix some other 2 variables to 0. So, if I am going to solve for 2 variables out of 4, the 2 variables that I am going to solve can be chosen in 4C2 ways, or they can be chosen in 6 ways. So, they can be chosen in 4C2 equal to 6 ways I can choose the variables. Now, these 6 ways by which I can choose them are written here from 1 to 6. So, one pair could be I am solving for x3 and x4, which means I am fixing x1 x2 to 0. I can solve for x1 x3 by fixing x2 and x4 to 0. I can solve for x1 and x4 by fixing x2 x3 to 0. I can solve for x2 and x3 by fixing x1 x4 to 0. I can solve for x2 and x4 by fixing x1 x3 to 0, and I can solve for x1 x2 by fixing x3 x4 to 0. So, I can solve 6 problems. I can choose 2 variables out of 4 in 6 ways, 4C2 ways that have been shown in this corner, and I can solve the problem using these 6 pairs of variables. In each of these 6 problems, there are 2 basic variables, the variables that we are going to solve, and we have the remaining 2 variables as non-basic variables, and we fix the non-basic variables to 0. So, those variables that are fixed to 0 are the non-basic variables, and those variables that we are going to solve are the basic variables. Now, let us look at each one of these 6 solutions and see what happens when we actually solve them. The first out of the 6 solutions, we are going to solve for x3 and x4, and we are going to fix x1 and x2 at 0. So, when we solve for x3 and x4, we are fixing x1 and x2 to 0. So, I am just striking x1 x2 off. Now, we can easily see that the solution is x3 equal to 21, x4 equal to 24. Because x1 x2 are fixed at 0, they are not going to contribute. So, we will have x3 equal to 21, x4 equal to 24, that is shown here as the first solution. Now, we move to the second solution. Coming back to the first one, we said we fixed x1 x2 to 0, therefore, we got the solution x3 equal to 21, x4 equal to 24, which is written here x3 equal to 21, x4 equal to 24. We now evaluate the objective function value for this, because this solution is basic feasible. So, let me explain what a basic feasible solution is. Now, this solution is basic because we have fixed x1 x2, 2 out of the 4 variables to 0, and more importantly we are solving for 2 variables x3 and x4. So, we are solving for x3 and x4, those variables are called basic variables. Non-basic variables are fixed at 0. We get a solution x3 equal to 21, x4 equal to 24, x1 equal to 0, x2 equal to 0. Now, this solution x1 equal to 0, x2 equal to 0 x3 equal to 21, x4 equal to 24 satisfies the non-negativity restriction of x1, x2, x3, x4 greater than or equal to 0, and also satisfies these two equations which are now the constraints. Because this solution satisfies all the constraints, it becomes feasible. Because it satisfies all the constraints, it becomes feasible, and since it is a basic solution, it becomes basic feasible. So again, a solution is basic when we solve for as many variables as the number of equations. There are two equations, two constraints, we solve for two variables. The basic variables here are x3 and x4. The non-basic variables are set to 0, x1 and x2 are set to 0. So when we solve, we get a solution x3 equal to 21, x4 equal to 24. Now this is a basic solution, and since this basic solution is also feasible, it satisfies this constraint, this and the non-negativity restriction, it becomes a basic feasible solution. Once we have a basic feasible solution, we find the value of the objective function. The objective function is 0 because both x1 and x2 are 0, x3 and x4 do not contribute to the objective function. So the value is 10 into 0 plus 9 into 0, which is 0. We now move to the second of the 6 solutions. We now move to the second of the 6 solutions. Now in this second solution, we are going to solve for x1 and x3 by keeping x2 and x4 to 0. Since I am keeping x2 and x4 to 0, I am writing these off, x2 and x4 are not here. So directly I get 4x1 equal to 24 from the second equation, that gives me x1 equal to 6. And once I substitute x1 equal to 6, 3x1 is 18, therefore x3 is equal to 3. So this basic solution, where we are solving for two variables x1 and x3, fixing the remaining variables to 0, gives us x1 equal to 6 and x3 equal to 3. This is also basic feasible because x2 equal to 0, x4 equal to 0, x1 equal to 6, x3 equal to 3 satisfies the non-negativity restriction, and therefore this is basic feasible. Now we evaluate the objective function value. So x1 equal to 6, x2 equal to 0 would give us 10x1 plus 9x2 equal to 10 into 6 plus 9 into 0, which is 60. So we get the second solution, which is here. We now look at the third solution. In the third solution, we are going to solve for x1 and x4. So when we solve for x1 and x4, we have x2 and x3 equal to 0. So x2 and x3 are now kept equal to 0. So from the first equation, we will get 3x1 equal to 21, we get x1 equal to 7. So when we substitute x1 equal to 7 in the second equation, we get 28 plus x4 equal to 24, x4 is minus 4, and therefore this solution is infeasible and does not satisfy the non-negativity restriction. So we write it as infeasible and we do not evaluate the objective function. We now go to the fourth one, where we are going to solve for x2 and x3 we are going to solve for x2 and x3. So, we will eliminate x1 and x4 here. So, we will eliminate x1 and x4 here. So, this would give us 3x2 equal to 24, and then we would get x2 equal to 8, which is shown here. Now, when we substitute x2 equal to 8 in the first equation, we get 24 plus x3 equal to 21, we get x3 equal to minus 3, and this solution is infeasible because it violates the non-negativity restriction. We now move on to the fifth solution, where we solve for x2 and x4, and therefore we will eliminate x1 and x3, From the first equation, we get 3x2 equal to 21, so x2 is equal to 7. Now, we substitute in the second equation, 7 into 3 21 plus 3 equal to 24, x4 equal to 3. So, this is basic feasible because it satisfies the non-negativity restriction. The value of the objective function is 9 into 7, which is 63. The sixth and the last one is we solve for x1 and x2 here by eliminating x3 and x4. So, we solve for x1 and x2 by eliminating x3 and x4, and when we solve for 3x1 plus 3x2 equal to 21, 4x1 plus 3x2 equal to 24, we get a solution x1 equal to 3, x2 equal to 4, which is also basic feasible. So, we evaluate the objective function to get 66, which is shown here, and 66 is the best solution that we have out of the basic feasible solutions, and hence is the optimum solution to this problem. In the next class, we will revisit this algebraic method, and we will try to get more insights into the algebraic method.